Let's again use the pain medicine as an example. In a hypothesis test with an extreme sample mean, there are two explanations for the extreme result. It may be because the alternative hypothesis is correct and the mean pain level of the new medicine is somewhere below 50, where such a sample mean would occur more frequently. The other explanation is that the null is correct and the extreme score is just due to random chance fluctuation. When a test is run, we are to believe the second explanation is true. When we calculate the test statistic and p-value, we're still believing that the new medicine's mean is 50 and it's no better than the old medicine, and that the result is just due to chance and tempting us to reject the null and accept the alternative. Once we have this final piece of evidence, then we decide which hypothesis to believe. With a sample mean of 47.7, there was only a 0.0329 chance that the null being true would produce such a mean. Therefore, we chose to reject the null and accept the alternative. Before we ever run the test, we should establish the alpha level of the test. This is the significance level. It is our predetermined limit we can accept with regard to making a type 1 error. 0.05 is the typical significance level. When we have only a 0.0329 chance of making a type 1 error, we accept the risk of being wrong and reject the null. The difference between the statistic and assumed parameter in the null is said to be a statistically significant difference if it creates a p-value that's below the alpha level or significance level of the test. If we were testing something where making a type 1 error had a greater consequence, we might choose an alpha level, a significance level of only 1%. Only a difference between the statistic and parameter that happens at most 1% of the time would allow us to take the risk and reject the null. The most common significance level is 0.05, but 0.01, 0.025, and 0.10 are also very common.